My name is Joseph Para. I was responsible for the design and hardware of our mobile simulated buoy hub project.
My name is Shyam Patel, and I'm responsible for the communication and software design of the project.
My name is Patrick Kelly, and I was working on the hardware as well as the control loop for this project.
My name is Tony, and I was in charge of the electrical components. So we're Team Buoy, and a little bit of a background to our project. So naval vessels, when they're on their missions, they can be out in sea for up to 6 months to a year. Now, during this time, they're susceptible to cyber attacks by, say, foreign governments. So in order to prevent against this, these vessels constantly need updates of the latest cyber patches. Now, it's wasteful for the vessels to come back to base, receive those upgrades, and then go back out to sea. So our solution to this problem is having a mobile simulated buoy hub. So essentially a buoy that we drop off at sea, then that communicates with the vessel so that the two VOs can autonomously connect with one another, form some sort of a physical connection such that the buoy can securely transfer all the data over to the vessel. Now, in addition to the vessel and the buoy, we also have this aspect of a headquarters, which will simulate as a laptop, which will display a buoy that gives, which displays a GUI that gives lifetime updates of the mission status and the buoy's coordinates.
For our buoy, we were tasked with designing something that was able to be sturdy in potentially turbulent waters like the ocean. It was very important that this be completely waterproof in order to protect sensitive electronics that were responsible for receiving file uploads from our GUI software, controlling the motors to get it to our destinations, and receiving latitude and longitude coordinates to get it to its next mission destination. Our timeline for this project began about 2 weeks in. That's when we formed our team and decided which project we were going to take on. After this, we defined our specific problem and generated as many solutions as we could, did our research, looked for similar projects. After this, we defined what each team member was going to be tasked with and responsible for. And we designed our preliminary design and wrote a bill of materials, basically what we were going to order, what we were going to manufacture. So with our parts and our materials, we began fabrication, and once we constructed a buoy, we began testing whether it would be able to maintain its, keep the water out and keep our electronics safe. While doing this, we were also constructing our GUI software and making sure that all the components could communicate with each other. After this construction, and after we had several designs under our belt, we met with the Naval Center, the representative from the Naval Center, Mr. Richard Carrasco. He gave us very relevant feedback about our design, about the mission itself, whether or not we were fulfilling the objective that we set out to do. And
So our project is relatively small. There's only the 4 of us working on it, but we still have broken down into 4 different subsystems and responsibilities. As we introduced in the beginning, Joseph has been working on the design of the physical buoy itself and the materials that we're using for that. I have been working on that as well, helping with that, as well as the control loop for the motors and how they're going to be programmed. Shyam has been responsible for the software, designing the GUI, and the communication with the laptop, how to upload files. And Tony has been working with the electrical components like the motors themselves, making sure everything functions properly with each other. For this project, we've had a few main advisors. Dr. Madi Mareth and Dr. Zach Casas are both from the Aspen lab here on campus. It's the Autonomous Systems lab. Dr. Madi Mareth has been working with us directly, giving us feedback and suggestions on how to solve this problem more effectively. And as Joseph mentioned, we have met once so far with Mr. Richard Carrasco, who is from the Naval Center in Corona, where they defined this project to begin with, what sort of solution we would be needing to come up with.
So in terms of the progress we've made this quarter, we basically have gone through a few different iterations of prototyping and manufacturing for our autonomous buoy. Our initial designs incorporated some speedboat type designs where we designed and manufactured a buoy which was more of an RC boat type of vehicle where it would be able to be given the coordinates and be able to travel quickly to that destination. After our meeting with Mr. Carrasco, we switched gears a little bit. We redesigned our buoy so that we could meet different mission standards. So we now have a more symmetrical buoy design, which is more representative of a traditional buoy, which is simply left out at sea in a static place. But our buoy is more dynamic. It has motors so that it can keep itself geolocated to a specific target location, regardless of whether there are currents in the water. So in terms of electrical design, we have 4 motors on the buoy. We control these motors using a motor controller board that's mounted on top of a Raspberry Pi. This Raspberry Pi is responsible for both data acquisition and control of the buoy motors. It also is responsible for the web server. In terms of the sensors that we use for the buoy, we have a GPS module, which is accurate within 5 meters of range. We have a magnetometer, a 60 OF magnetometer, which can give us details about accelerometer and heading. So we use the heading in our code to allow the buoy to calculate which direction it needs to move given a target coordinate system. For the Range Operations Center, we have a GUI, which is actually created on the Raspberry Pi, which is mounted on the boat itself. The way it works is the Raspberry Pi sets up a web server using Flask, and from the ground station, as long as they're connected to the same wireless network, we can monitor all aspects of the buoy. So here we've got a sample of our current autonomous buoy GUI. So we have, as you can see, we have indicators for motor status as well as the current motor power output. In the future, what we do is simplify this a little bit. So if we know that it's 89% left, 56% right, we'd be able to simplify that to whether the boat is moving left or right and at what velocity given the accelerometer readings. We also can see the buoy heading so that we can monitor which direction the buoy is going and to make sure that it's going in the right direction. As you can see, we've also got a target box, so this allows us to input a target coordinate to the buoy wirelessly, and then the buoy will be able to receive this coordinate and set that as its target so that the buoy could then go out and traverse to the target. We also have the current target for the buoy so that we can see where it's going currently and then update it if necessary. We also can see the current buoy location in terms of its longitude and latitude so that we can monitor where exactly the buoy is. This is all, again, using a Flask web server, which is hosted on the Raspberry Pi on the buoy itself. And this allows us to have a bidirectional communication so that we can not only tell the buoy what to do, but we can also, in real time, monitor the different aspects of the buoy without having to refresh continuously.
So just to summarize our project so far and the progress we've made, we have worked on a few different prototype designs of the buoy and decided on a symmetrical hexagonal design, which we have constructed, and we are in the process of testing with the motors and the necessary sensors and code to run everything together. We plan on continuing to test this with the PD control and motor loop program to autonomously navigate to our set coordinates and then maintain that location. We might redesign the buoy further if we think it could be more stable to withstand waves or potential hazards in the water to keep everything watertight on board. We want to test it in the water itself to make sure all of that holds up. And we also plan on coordinating with the other team who is designing the vessel itself, which we will be communicating with and transferring files to make sure that they can effectively communicate with each other and handle the necessary file transfer between the two vessels, which we think should be about 1 gigabyte of file. So this is our progress so far, and thanks for watching our presentation.